If you just got your brand new Boolean algebra simplification problem, relax. This is going to be easy. Hey everybody, welcome back to another video. Today we're going to be going through the Karnaugh method, or you may sometimes hear me call it the K-map method. I'll use the terms interchangeably. Now, if you're not too sure what the K-map method really is, you may be more familiar with a mathematical approach to simplify the complex Boolean expressions. Well, if you're watching this video, you probably may be struggling with that altogether. So hopefully this will be a gateway to you learning a much easier way to do the same thing at the same time. Now, what a Karnaugh map is, or a K map is that it represents the contents of a truth table as a grid or a map. Now, one thing you ought to know about truth tables is that in the truth table, you often get to see the results as to how they all end up. Let's go ahead and prepare the truth table for this expression first off. Now, if you want to take some time to do this by yourselves, pause the video and come back when you're done. Okay, here we go. I hope you got the same answer as I have for the truth table. Now, let's build off from here on constructing our Karnaugh map over here. So, um, the one thing that we'll have to take note of is the results from here, from this, say, I, I shouldn't be saying the expression here, I should be saying equation, since we have being equal to all this, right? Now, yeah, as I was saying, we need to focus on this part right here. So, what's important here is at which combo does it give the one values, the on values. And these will serve the basis for our next thing to do in the Karnaugh map. All right. Now, based off of what's given in all here, right? These are essentially just A bar B. This one here is A B bar, and this one's A B. Now, you don't really need to identify this right off the bat, but if you're given just the truth table, it's crucial that you know which one it is, so you can plot these out inside the Karnaugh map. Now, speaking of which, I've been babbling a bit for too long. Let's go ahead and construct the Karnaugh map. So the way you want to do it, right, is make it look like a grid. So your Karnaugh map will look a little bit like this. So I'm just gonna construct a simple one like this over here, right? And the placement for A and B here, they don't really matter, but I'm just gonna run with this. And I'm just gonna put A bar and A here, B bar and B here. I'll explain the logic behind how I decide what needs to be placed in here and in here. Okay. Now, one thing that you have to know is the ones. I mentioned that already. Okay, so based on what we have here, we're gonna plot out where about the ones appear. So if we're just looking at the expression here in which x is equated to, we look at the first term, AB bar. So the way you want to do it is this, A and B bar, right about there. So this is the spot where I'm going to be placing my 1 right here. Then we do it for the rest of the other expressions. So for A bar B, it's going to be A bar B right here. So I'll plot in another 1 right here, and AB, this one right here. Now that's really just it. The rest of the unfilled cells, you place a zero inside. Now, we're focusing on the ones here. The way how we simplify expressions using a Karnaugh map is by looping the ones together. There's a rule behind this, but one of the rules is that you need to be able to loop a certain number of ones to make it as one group. Then after that, from there, you can determine what these loops represent in terms of the terms wise. So I'm just going to use the green color over here for this one. Let's look over this one right here. Now looking at this, right, we determine the nature of it being as such that it encompasses the ones that are located in the A row, but spans across both the B's, both B's right here, the B bar and B. So when it spans across these two over here, right, we omit the term. So in a sense, this loop that I put in over here represents A, just A only. Now, if I were to loop this one next, this one here makes it so that, right, you're looping the ones that are located within the B column. But as far as A is concerned, it spans across both A bar and A. And as it spans across both these A's, you don't write the A terms at all. So in here, we put in a B. Now, having said that, we're pretty much done with the Karnaugh map already over here. From here on, all that's left is to write the simplified expression. Let me just write down simplified expression here. Now the simplified expression here is equal to A plus B. What we do is at the very end is whatever expressions that we've identified from here, we're gonna need to add them together. That will form the basis of our simplified expression or simplified equation. Sorry. Now, just to take away from this a little bit, the main difference behind an expression is that an expression is just an expression. It doesn't have anything that it's equated to. Like there's no left hand side, there's no right hand side from there. Once it gets equated, it's such that you have a left hand side and a right hand side, that's what we call an equation. Anyway, this is the final answer for for this example right over here. So what are the rules behind this actually? That's what some of you might be asking while I was demonstrating the recent example. Well, there are some ground rules, and I've laid down what I consider to be some the more crucial points that you ought to take note of. Let's go ahead and talk about how I've decided to write down the expressions from the top and the bottom down. You might have noticed that I wrote something a lot like this, where I just put in the bar value first before the original value. Now, the first rule behind constructing a Karnaugh map is that when you're preparing this say part right over here, you're going to want to follow the order based on the gray code rules. Now, the gray code rule states that at least for single expressions like this, you have to start off with the 0 value followed by the 1 value next. Now, in our case, if we wanted to put in, say, A bar and A, you're gonna need to put them as such. You have to put the barred version first before the regular version. Now, this ties in with simplifying expressions that involve two different unknowns. But later on in other examples, we'll be seeing how to construct a Karnaugh map using well, with with three or four different unknowns tied in all together. So when that time comes, let me just erase this off. You're gonna want to take note of this one here. This might be a little bit confusing at first, but say for instance, if you want to put A, B together in the same row or in the same column, you see this in action once you get into the next example. So if you want to put the order in which how it is between A and B combined together, you're gonna need to start by having both of them barred first, followed by A bar B. Notice that it follows wherever the one is, it removes the bar straight off. Then after that, the next thing you have to put in is AB, which corresponds to this part of the gray code, and then AB bar. This is something like a pattern that you're gonna need to be able to get used to. For all my examples, we're only really going to be dabbling with either one or two unknowns on one side. If you want to dabble with more than that for our four unknown expression problem, then by all means go ahead. But it's gonna get a little bit more complicated, and it's just gonna be too dang long for that. Now, as you also may have noticed, we only took into account the ones. So wherever there are zeros, those are none of our concern. Just a reminder, the ones represent each of the sum of product terms which are being added together, right? And the way how I've grouped them along either a row or a column. But in later examples, you may see that I would resort to using a loop that spans more than a row or more than a column at the same time, in which I would just call a rectangle or a quadrilateral, whatever rocks your boat. This only applies for if, I guess, three unknowns or four unknown expressions. If you see this in a two unknown expression problem, it just means something a lot like this here. Just looping the whole thing, which means that no, the whole thing is just one itself, which means that the whole thing encompasses the full thing. It's true. And there's more to the size of the loop or the shape of the loop actually. The loops that I made were of size 2. In effect, when you're trying to solve a K-map problem, you're going to need to make sure that your loops are of sizes that correspond to the powers of 2. So you either have loops that are size 2, size 4, size 8, and so on. This doesn't mean that you can simply just loop howsoever you wish. So say for instance that your let's just say you have something a lot like this here. Looping it this way is not the right way to go. Okay. You're gonna need to put them in with as is, like how loop them in twos, like that. Now, when you're looping the loops inside the Karnaugh map, you're gonna need to make sure that they're as large as possible with not needing to overlap as much as possible. There are times like how it was just now when looping happens with overlaps, like how it overlaps in this one right here. The only time that when you really need to overlap is that when you have a loner one, you're gonna need to dabble with perhaps maybe just a loop, something like that, right? This can probably be the most confusing part about the Karnaugh map method, as I would say. But over time, as you practice, I suppose that you should be able to get that down pat. the groups may overlap within the above rules, and as I mentioned, one lone ones can sometimes mean overlapping of the loops right there. And finally, the final Boolean expression can only consider those values which remain constant within the group, that is, remain at 1 or 0 throughout the group. Now, this here pretty much formalizes the explanation that I did when I was rationalizing how I read the loops in the recent example over there. So from there, it's more of like you have to see where it encompasses, like whether it encompasses whether the loop goes through both variants of an unknown's regular self and its barred version, or whether it just falls within just one version of the expression itself only. So yeah, now that we've laid out the rules that you need to keep in mind when creating the Karnaugh map, let's go ahead and get on with another example. Right, in this example, we have another some products equation over here, but it involves three different unknowns, namely A, B, and C. The way how we want to construct the Karnaugh map method, the basis that still remains the same, but you may notice that the Karnaugh map will end up being a lot longer or a lot taller. It depends on how you craft them and also how you arrange your unknowns over here. Now, see if now with this, it opens up a lot of opportunities to look at different ways to create your Karnaugh map. Let me go plot out two different ways that you can plot out the Karnaugh map for this one. So the way I normally like to go with this is that, oh wait, let me use orange. The way how it is that I usually like my Karnaugh maps to remain just as long as I remain not as tall, but it doesn't really matter as it goes across. Now, here you might want to take note. Remember the order based on the gray code that we have to, you know, put in. We first remove the bar from the last term, remove the bars from the first term, and then place the bar back in the last one. Okay. Just gonna preface this by putting in the 0, 0. No, that's a bad idea. Hold on. Yeah, just putting in the 0, 0, 0, 1, 1, 1, 1, 0, and then 0 and 1 here. You may see certain examples that would say you just need to put in the zeros and ones and then 0, 0, 0, 1, 1, 1, 1, 0. But I believe this will be a bit more clear as to what you're looping against, right? So this is all there is I'm going to be doing for now. Okay, let's start putting in our ones into this Karnaugh map. No, wait. Let me show you another way on how you can craft this out. This isn't the one that I'm going to be using, but if it rocks your boat, then sure. Our C just remains as is, just bar C and then C. When it comes to A, B, you've got a bar in both of them first, followed by the one with just A being barred. Then A, B alone, A, B barred, finally. So this is another way that you can construct your Karnaugh map. It really is up to you whether you prefer having a taller Karnaugh map or a longer one. It doesn't really matter as long as you arrange the terms on on this side and this side properly. Okay, now let's come back to this one. So A bar, no, sorry, A, B bar, C bar. So we're looking at A, B bar, C bar. So you're going to put in your 1 right here. Next up, A bar, B bar, C. So A bar, B bar, C. So you're going to want to place this right there. And then next up we have A bar, B, C. A bar, B, C right here. And then finally, A, B, C bar. So A, B, C bar right there. Okay. So this is just there. And then we'll go ahead and loop up these ones right here. Let's go ahead and pull our loops. So I can see 2 different loops and they both don't overlap with each other, which is totally fine. But one of it might be a little bit hard to see. Now, the first one that I want to loop is these 2 right here. Now, going by what I mentioned about observing whether they stay constant or not, let's look at it this way. It stays within the A bar column, which means the term does include A bar inside. But as far as the column goes, see, C remains the same, but B is the one that changes. It goes across with the states being different. So we don't include the B term inside, we just include the C. So this green loop here represents A bar C. Next up, we have this one here. This is a special loop. In a way, it's like you gotta remember that whatever borders that you put up right here, they don't necessarily serve the ultimatum for like what goes beyond this one here doesn't exist. Well, typically, if you're drawing out the Karnaugh map properly, you're gonna want to make sure that you box it up properly. But in this case, I'm just gonna leave it as is for now. Now, with the Karnaugh map being as such, you can see that we can still apply the same rules. So it goes across the A column right there. But as far as the A row, sorry. But as far as it goes across the columns, B still changes, but it remains constant at C bar. So like earlier, we omit the B term, but we put in C bar inside. So with that, our simplified equation will be equal to A bar C. X equals to A bar C plus AC bar. Now I can always go ahead and try it out inside a different Karnaugh map according to how you have. Yeah, let's see if we can get this one right. Pause the video if you want to try your luck with this this Karnaugh map over here and see whether you get the same answer. And then it will see the correct answer in a bit. There we go. So, did you get the correct answer? Great. Let's go ahead and try out another one. This time with 4 different unknowns. So this example over here, you may be tempted to try and put 3 unknowns in either the rows or in the columns, but I strongly recommend against that. But if that's what you really want to do, that's okay, I guess. But my Karnaugh map for this one, it's gonna be as compact as I can. So what you're going to be seeing here is that it's going to follow in as a regular square, just larger than the first example that we did earlier. I'm going to put A, B, C, D here. Now, if you're wondering whether you can just mix them up and put them in like this, sure, no problem. You just need to make sure that whatever that you put up over here and here adhere to the way how you count up in gray code. But for simplicity's sake, I'm just gonna go ahead and use the conventional way of just putting in A, B, then C, D like that. Now, as the gray code states, you have to put all bars on all the terms first. Then the next one just has the bar on the first unknown. Then no bars at all. Then the bar on the second term. Again, same thing up here. C, D, both barred. C bar D, C D, C D bar. There you go. So this is gonna serve the basis for your Karnaugh map in this one. Of course, if you do decide to mix up the terms altogether, see whether you can get the same answer as what I've derived out from here at the end. Now looking at this here, right? The first one that we have is A bar, B bar, C bar, D bar. Ugh, mouthful. Looking at the spot here. So we'll put in a 1 right there. Then next up, A, B bar, C, D bar right here. Then next up, we have A bar, B bar, C, D bar right there. And then next up, we have A, B bar, C, D bar, which gives in right about here. And then we populate the rest of them with just zeros over here. Now this is one tough nut, because it seems as if the ones are all spread out all over at the four corners. But what if I told you that you could loop them up into one big loop, like as shown over here? Shocking, isn't it? This kind of extends the part where I mentioned that sometimes you can say that whatever goes beyond goes beyond, like it's not constricted within the borders per se. So this one here, let's look at it. Let's look at it from the row perspective. It says constant at B bar over here, but it changes from A bar and A. So this one here doesn't have the A term. Instead, we have the B bar term. And as far as the columns go, it stays constant at D bar, whereas it goes across C bar and C. So we don't include the C term inside, we just put in D bar here. Remember, B bar D bar is not the same as B D bar the whole way. Refer to De Morgan's law if you're not entirely sure about why these are not the same. Okay, so that's really kind of just it. That's really just it. Your final expression, simplified expression or equation per se, is x equals to B bar D bar. Now this is a very simplistic example over here. So these kind of give off one of these exceptions, or one of the more weirder ones to dabble with. We're gonna go visit that one in a bit. Here we start talking about the weirder or the more peculiar situations where you're gonna need to think of different solutions to the Karnaugh map problem. Like in the recent example that we did just now, um, we've got these ones over here that can be grouped up, you know. That kind of just serves up as per se, it makes its own loop. Now, expanding on the fact that you can see that the range is infinite as is, it's kind of like if I were to add on to the rows over here simply just because, um, counting up in gray code just looks a lot like this here, which means we're basically just replicating this grid over here in the same place. And when we see that they're duplicated, right, we can say that it just groups up outside like this. And the same thing can be said about the rows over here. So this can be a bit hard to visualize, but these are one of the few peculiar ones that you will need to take note of. At the end, like earlier just now, the expression they get, the simplified expression they get is b bar d bar. Following that, let's go through another peculiar example. So over here, in this Karnaugh map that we've got here, I can see that we can draw up two different loops. The obvious one would be this large rectangle that we can go across right over here. And then we have another one that just comes off like this. We'll get that one we'll get to that one in a little bit, but for now, um, just looking at this over here, what we have is that it goes across row-wise A bar and A, but B remains constant. So B becomes part of this simplified term for this loop here. Whereas for the columns-wise, it goes across both C and D in not a constant fashion. Like it goes across C bar and C in certain places and D bar and D in certain places as well. So we don't include either one of those. And we're just going to call it B. That's it. That's it for that loop. Now notice that at the very end, you have this loner one over here. In normal circumstances, you want to try to find ways to get the largest groups as much as possible with as few intersections as much as possible. But in this case here, we have a loner one. So we don't really have much of a choice but to just loop it up like this right here. So looking at this loop here, it goes across A bar being constant, but B bar and B, the B bar and B are changing. So we don't include the B term, we just put an A bar there. And as columns wise goes, it just falls on C bar, D bar constantly. So it just becomes C bar, D bar here. So at the very end, your simplified expression for this one is equal to B plus A bar, C bar, D bar. I'm not supposed to put the X here because it's not been established that it's equal to X all the time. Yeah, so this is one of those other peculiar situations whereby you're gonna need to ensure you know when you need to overlap them. You try to get the biggest group as much as possible. Putting in just say a group like this instead, like smaller groups of four, they don't really count. They don't really compensate because like I said, you got to try to find the largest group as much as possible, with as few intersections as much as possible. But you gotta know to make sure that the size of the loop always adheres to 2 powers. That means 2, 4, 8, 16, and so on, right? Going on with this example here, let's go ahead and make use of what we've went through in the past to peculiar situations and apply it over here. So in this case, you might be tempted to just loop up the groups of 4 this way. However, I'd say the more appropriate one would be with this weird loop over here. Because, it can be seen as just, you're going across infinitely as much as you can. And if you look at it this way, it just shows that, well, by row wise, it goes across A and B both being barred or not. So we don't count any of those. But as far as columns goes, these D bars are the only constant thing that's in here. So at the end, this is this here is your simplified expression. And again, we have one other example where it goes across. You have to take note of the fact that the space can go off infinitely as much as you want. So in here, you can draw your loop like as such over here. So in this case, well, B bar stays constant, whereas A changes a bit, and it stays within the C bar D column. So at the end, this loop here refers to B bar C bar D. That's your simplified expression for this one. Go ahead and do one more example. So in here, I've got another 4 unknown expression or equation over here, with a few more sum of product terms involved in here. So maybe take the time to try and solve this on your own, and come back in a few minutes time, to see whether your solution kind of ends up looking like mine. Remember, it doesn't really necessarily mean that you have to draw or not draw, label the Karnaugh map the same way as I do. But as long as you're able to derive out the same answer at the very end, then I guess, well, it pretty much works out. So yeah, I'll see you in a bit. Okay, welcome back. So, let's go ahead and fill this Karnaugh map up. I'm just gonna put in W and X here, Y and Z here. As far as the gray code is concerned, you put W bar, X bar right there, W bar X, WX, WX bar right there. And then as far as YZ goes, Y bar Z bar, Y bar Z, YZ, YZ bar right there. Okay, so let's fill up the ones next. So W bar X, which corresponds to this row, Y bar Z bar, which corresponds to this row, right? This column, sorry. So it goes around there. Now next up, we have W bar X, again, right, this here, and Y bar Z here. So it goes across this part there. And then WXYZ. So WXYZ over here. WXYZ bar. So WXYZ bar right there. And then WX bar YZ. Right there. And then W X bar Y Z bar. Which goes in right there. Now these are isolated loops that we'll be drawing here. So the first loop, we'll look at this large square that we can draw up over here. So for this one, we have W being constant, but it goes through X and X bar. So we don't write in the X term, we just put in W right there. And as far as column goes, Y remains constant, whereas Z changes a bit between Z and Z bar. So this green loop here represents WY. The other loop that we can draw up is this one right there. So in here, it stays within the W bar X column. So put W bar X, and it stays within the W bar X row. So we'll just put in W bar X. Then as far as the columns go, Y bar remains constant, but it goes across Z bar and Z. So we omit the Z term and just put in Y bar right there. At the very end, your final equation should be F equals to WY plus W bar XY. And here we go. This is just another example that we got over here. Okay, I think I've dragged on the video a little long enough. Let's end it off with this example over here. Now, before I show you the solution to this example, I want you guys to try it out on your own. I will give you guys about a few minutes to try this out. And I'll see you guys in a bit. Okie doke, let's go ahead and finish this up. So I'm going to put PQ and RS like I've shown over here, but feel free to mix them up as however you wish, but ensure that whatever you write down in here adheres to the grade code rules. So you start off with P bar Q bar here, P bar Q, PQ, and then PQ bar right there. As far as RS goes, R bar S bar, R bar S, RS, and RS bar. Start placing in the ones. So P bar Q, R bar S bar, right there. So put in the 1. Next up, P bar Q, R bar S, right there. Next up, P bar Q, R S. So up in the 1 here. Next up, P bar Q, R S bar. Put this one in here. And then P bar Q bar, R bar S. And then finally, P bar Q bar, RS. Pop in the 1 right there. Then we'll just place in the zeros on the other unoccupied cells. Okay, now again here, we're gonna need to draw in 2 loops this time. It just so happens that the recent examples that we have either can be solved with just 1 loop or 2 loops. It kind of really just depends on how complex your expression is to begin with, but if you're able to simplify it in as few loops as possible, then I guess that's all right. We're gonna need to keep in mind that we should be drawing as many large loops as we can with as few intersections as much as we can. But sometimes, if it means drawing up a bigger loop, you know, you may need to consider intersections in our case right here. So let's go ahead. Let's draw up one right here, it stays within the p bar q column, p bar q row, but it goes across R and S both interchangeably between the regular and bar counterparts. So this green loop here represents p bar q. And then here's where we overlap a bit, but all in the name of trying to get as many big loops as you can. So in here, we're not dabbling with just one lone one here, but two lone ones. By themselves, you can be tempted to just draw out the loop this way, but it be daft to try not to get the bigger loop in it while you still can. So that's why I end up drawing the loop right over here. Now, as far as the coverage in which the loop goes, it goes across P bar constantly, but Q and Q bar interchangeably. So we don't put in the Q term, we just put in P bar here. By columns, R and R bar, it goes across the R terms interchangeably, but S remains constant. So we put an S here. So at the very end, your final equation should be F equals to P bar Q plus P bar S. Now there you go. That's the answer to this example over here. And yeah, that's all there is to the Karnaugh map method. I hope this has been helpful. If you have any questions, you know where to reach me. My name is Oscillo. I go by the Zombie Dude, and I'll catch you guys in the next one.